So now it's for opponent to challenge the reporter for the problem. 1 minute.
Okay, we'd like to challenge choosing characters.
Which problem?
Number 16. Choosing characters.
We would like to reject.
I'd like to challenge problem 10 here. Number 10.
Oh. We would like to accept.
So please write down your name.
该你给你一个整齐的工作环境，效率很高。Yes， 都很行。
You're ready? So, time's up. So please start your report.
Hello everyone, I'm Zhang Renzhe and I'm going to present the problem 10, magnetic gear. The problem statement is about there's several identical features spinners and blah blah blah. And there's some words with different color. There are the words the words we consider as focuses. The key questions are: question 1, how may the magnetic field affect the motion? Question 2, what may limit the couple rotation? Couple means in this the couple. Okay. Observation. If you just like the video, the velocity of two spinner change alternately, and the rotational kinetic energy is transferred from one spinner to the other. Notice the left three magnets and the right ones have different magnetic moment direction. Sure. Observation, each one includes alternating the rotation. And the video, the velocity of two spinners also change alternately individually. But look, the direction changed. Oh, wait. Stop playing. Yeah, well, the left three magnets and one red ones have the same magnetic moment direction. When one rotates too fast, the other spinner cannot catch up, like this. So like this, and the other spinner will be with rotational angle oscillation. Theory. There are 2 points on the plane. Point O means the place where the magnet was put. We want to calculate the magnetic potential at point P. We set S as the distance between the axis, M as the moment at the magnet, and A as the radius of each magnet. By using Biot-Savart's law, the magnetic field can be expressed as the function. Because of the definition, then the magnetic potential can be expressed as the second function. There's a spin rotating on the plane. We define I as the moment of inertia, omega as the angular velocity, and the kinetic energy is it. Total energy. The total energy of the system is expressed as the equation, where delta E means the loss energy caused by friction. Dynamic function. The magnetic force, Fbx. There are two magnets. One is still, and the other moves directly. The differential of the potential, the force caused by magnetic field, can be expressed as a function. Sigma means adding potential of each the two magnets. This, and this. And there are two magnets. One is still, and the other moves direct to the still one. The relation between the distance and the force can be expressed as a graph. R is the radius of the magnet. there a spinner with magnet and steel magnet, the force between them can be expressed as the upper graph. Angle and force, the moving angle and the force. And if when the spinner rotates too fast and with rigid the angle, the velocity, the force will be like the lower graph, time force. Experiment. It's all set up. It's all experiment device. We stock the two spinners on paper. Each separated in a rigid systems, where the two spinners did oscillate vertically. Okay, then we put the servo on the holder and ensure that it didn't shake. First, we want to ensure the relation between moving distance and friction. Then we let the spinner rotate without another magnet loaded, and observe the angular velocity to calculate the kinetic energy. We put the steel magnet and the spinner with steel magnet. Rotate the spinner and observe the velocity, the angular velocity and distance between the steel magnet and each one rotating for confirming the energy equation. We also wanted to know how fast the rotating spinner can make the other steel. So we gave one spinner a high original speed of 30 until the other spinner rotates. I then wanted to confirm the period relation and repair the phenomenon. We put two spinners as the statement of the problem, then observe them. The part of analysis. That one. We define S as a moving distance, as we found the kinetic energy it declined linearly in place with the moving distance. And we could just take the differential of the straight line of those energy, and we found the friction is a constant. In the system, it only has kinetic energy and loss energy. And the alternate change between potential and kinetic energy. The blue line is potential and the orange line is kinetic energy. They can measure all the theoretical model because and the decrease of kinetic energy is about a linear straight line, and so it can also confirm that the friction is constant. As the line indicates, the touch spinner rotated in the moment when level on the line and oscillate in the right moment of the line. In this time it rotates. In this time it oscillates. And the oscillate of the other, in times it oscillates, and then they rotates, then oscillates. In data, we observed that there boundary line and paint green. The left side of the line has higher kinetic energy of touch spinner and high uncertainty. And the right side has low kinetic energy and of the touch line and lower uncertainty. In this area in this area, the untouched one is oscillating. Was oscillating. Okay, so without that, it's oscillating thing. When one oscillates, the theory, the theory doesn't work. When I oscillate. Conclusion. How may the magnetic field affect the motion? Answer is an equation. So yeah. We define x as moving distance. X as moving distance, omega as angular velocity, s as the distance between each two magnets, and as the theory of and its theory told us, direction can be expressed as the equation, just like the theory. So, what may limit couple rotation? As I observed in case of experiment 3. Let's spin the rotator after it depends on the velocity. It's just like the case in experiment 3. It should be in a range. That's all. Thank you.
Okay. We're opponents and we're actually questions. Can we take a look at the gear?
Look at gear, here, and here. But be careful because it's not. It's dirty now. And
it's metal here, right?
right.
So I think the metal will influence the magnetic field, right?
But I don't change the gear's metal. I don't change the metal of the gear.
Okay. And hey, turn to page 24. Turn to page 24. And
24.
why did you say it matches 0?
Cause it's
Sorry,
because they have the same period, and we can add it together by add it together to get the straight line.
So it is the fixed magnet and a spin magnet here, right?
A what?
A fixed magnet and a spin magnet
right.
here, right? Okay, so I want to see. Okay, next.
A fixed one and 3 rotate one.
Next. Turn to page 26. How do you think your energy, your total energy is you draw a line off?
Okay, time's up. We stop. So I'm going to prepare 3 minutes.
这个仪表对，哎，这个仪表对。
Okay, time's up. 4 minutes.
Okay, I'd like to summarize the report. And this is a main gear. We see as a gear, if you place them side by side on the plan, you remove one of them, the remaining one starts to relate only due to the magnetic field. Investigate and explain the phenomenon. And the task of this problem is to activate, to do an experiment, accurate, reliable device, and complete explanation of this phenomenon. And you need to analyze, and the simulation of motion should be considered if you want to make sure your model is great. And this is the summary of the report. We see the device meets the requirement, and we see the device of the experiment and some theory about the magnetic field, which is a function of the position, and experiment to find out other parameters like friction. Okay, these are some pros and improvements. The pros is that they show the effect of the magnetic field, and the graph to show that forces the energy, and consider the friction effect is great. And these are some improvements. That of Fluent's presentation and need a clear explanation of the magnet setup, and overcomplicated diagram with too many data in one chart, and some other consideration about this phenomenon. Okay, we'll start our discussion. Let's start our discussion. What to do? Just spin, and that one magnet gear release, and don't keep spinning them like a roll gear. A roll gear will spin continuously. Right?
You mean
the gear will spin, roll gear will spin continuously and keep affecting another gear. Not like I push one gear and another gear just spin because of that.
yeah, it can rotate and spin and just spin, but cannot keep this for a long time.
Okay, so your experience is just push one and another oscillate or rotating because of that. And okay, then next question. And can you then go to the page that describes your theory? Describe your magnetic field theory.
到了理论那一页，就在力学昨天手那一页，上页，在我上，它都是往上。再往上，对，这个 K up，因为 it's K。
Right. Why K is an unknown constant? You know the M, so you can know the K, right? You should know if you know the M, you should know the magnetic field out. Should we can I use the blackboard to discuss? Okay. I think if here is a non M, you know, the magnet moment and we can calculate the magnetic field over here. This is R and this perpendicular. Okay, so I know here's a function mu naught this M3 R M dot R and minus M R squared over R cubic R. Okay. So I think it's possible to calculate the R and calculate the K by comparing this single moment and with your formula. We can get the K, right?
Theoretically, yes, but I didn't do that.
Okay. Thanks. And let's go into the potential energy. Potential energy change. The measurement of potential energy. You measure potential energy, data changed by time. That's it, right? Okay. The yellow line is the total energy, right?
Right.
Okay. And point does it go down and go up and go down and have a lot of peaks? How do you think about this?
It may be caused by the little horizontal oscillation.
So you say what?
Little horizontal oscillation.
Hard.
Horizontal.
Okay. Then you did do a line to describe your yellow energy, total energy data, right?
Right.
Okay, then why you can just draw a line there.
Drawing
A line of total energy.
Approximating, right?
Of total energy.
Of total energy. You mean
The y equal to 2.15x plus 85.849. That yellow data, the energy they have. Do you know what I mean? The data of energy changed by time. Okay, you draw a line and your conclusion, that will be the conclusion point.
oh
This is the left one is the potential energy plus the kinetic energy and equal to a linear relation to time. I think that's not x, it's t, right? That.
you mean which is T?
No, this should be t, not x, right? This C3x. I think this should be C3t because we use the blackboard again and this is your energy in the time. It's like this, and you draw a line, and you may think it's like this, right? So it's
If the function is like, but if the ft is like that, it almost straight.
why the angular velocity. What is x? What did x mean?
The moving distance.
Distance. If this oscillating, why the distance will be like this? Oh, okay, I know. know what you mean. Then, but why you solve the axis diagram a straight line if the velocity is not the constant? Velocity is not the constant, right?
What is not?
Velocity, angular velocity.
Angular velocity is not.
The constant. I thought this is not xt diagram, it's beta t diagram because it's a rotating, right?
Right.
So I'll change your energy. The total energy is equal to initial energy minus tau beta. Tau is caused by the friction coefficient, and the beta is the angular right moving angle. So I think it's a greater form. The initial energy minus tau beta is a greater form to describe the energy energy change. Then okay, then move to our last part. Let's show the energy data again. The conclusion of energy. The s to the power of -3.
You mean we minus the power of s?
Right. Why -3? Why the magnetic potential energy is proportional to s to the power of -3?
Because it's based on energy.
But I don't think the energy will be s to the power of -3, right? The force of the magnet is equal to this is the potential energy of the magnet single magnet dipole inside the magnet field, right? This magnet.
Right.
So, okay. Okay, I know that. So, so I'll change this into L and B. So you use this formula to find out the M dot B is proportional to the R S. The S. You mean S is the distance between two magnets, right?
Between two magnets, there's the axis of two magnets.
Right. So you need to do the sum.
I calculate it like this.
Right. You need to do all the.
Ready?
Right. So your conclusion is to the magnetic field affecting motion is to describe your energy, the description of your energy. Okay. Anyways, I don't think your let's turn to the energy changing by time. Right. Next thing. I don't think it will have a linear relation between time.
Sorry, time is up. So open the summarize. 1 minute.
They didn't say what we asked at the first question, and the K should be calculated after this discussion. For the potential energy measurement, we know that they do sum of different magnets. Potential energy is measured like that. Okay, but I thought it is not very accurate because of the energy is not quite great, quite easy to describe. And for the fifth, I think they need to change the conclusion into the actual part of magnet 3 and do a sum. Okay.
The question reviewer.
要带的这个
3 minutes.
So, first of all, I want to ask the reporter, do you assume that your whole magnet is just a power source?
It's the whole system.
What is it do?
I think it's great. The magnet is like a current. So he used the radius of magnet A, and assume that there's a current.
So please turn to page 26. So I see you have a trend line right here. Could you explain what this trend line is?
Oh, left the. Oh, this one. I mean, it's approximating. It's approximating the line.
So what do you mean? Why you draw this?
And I think this is great. As I finally say that it should be EI and E initial, the energy initial, and minus tau beta. The energy should be like this.
So I will have a question about your experimental method. So did you spin it with your hand, or did you use something to control?
Okay. But I use tracker to check it.
Okay, so
So
you
check
think that this is a good method to start?
Yes.
Since you-
They need to fix the initial energy. So I think it's not quite great because we need to control the finger will not continuously spin this, so it should be a very short time for one.
So my question for you is, you know that equation for friction is mu k times the natural force, right? So as the spinner is spinning, the repulsion of the magnets will change. So the natural force will change. So the friction will change. In theory. So how do you explain that?
The friction will change with what?
Okay, I can ask the opponent. So do you get what I just asked?
No, I thought he should do the experiment with one. There's magnets, and with one fixed magnet. They should do the experiment with one magnet here plus fixed magnet, and analyze the consumption of energy and find out the friction with the fixed magnet and without the fixed magnet.
Time's up.
都水跟酒喝吗？我会渴死。感谢评审。两百整。 带。这是昨天下面我公司的，才放在这里做。
Time's up. So 4 minutes.
先休息，先空白话。
So hello everyone, I'm the reviewer from Team Chaco team, and today I'm going to talk about magnetic gear. So first, as for the reporter, he has a clear observation video, and he also highlighted some main points in the problem statement. He also has numerous experiments to prove his theory, and he combined graphs to analyze his results. But however, there are some areas of improvement where he didn't quite answer the problem statement, and he doesn't really explain the theory very clearly, and his experimental setup needs some improvement. And most of all, we think that the data graph was confusing to understand, and the units in the graphs weren't also labeled. And okay, so he also lacks the explanation in the experiment and the quantitative results, and his presentation needs to be improved. So as for the opponent, I think he has understood the reporter's presentation pretty well and mentioned some flaws in the reporter's presentation. And he understood the main focus of the problem statement and analyzed and discussed the unit during the discussion. However, I think what the opponent didn't achieve is some problems in the reporter's presentation was not brought to attention. And he also was too focused on the theory and lacks the explanation on experiment itself. So as for the question part, the opponent first asked whether the metal will influence the magnetic field or not. And the reporter answered, we changed the gear in the fidget spinner. And next, the opponent asked that the main focus of the problem should be that the phenomenon acts like a gear, continuously spinning, but the reporter didn't give a clear answer. And then the opponent asked that K should be a known constant using the formula of magnetic leverage. The reporter replied that it's possible, but wasn't mentioned in the report. And the opponent asked that why was there a trend line in the data of the energy and time graph. The reporter also didn't give a clear answer. And the opponent next asked that he disagreed with the reporter that he viewed the magnet as a point. The reporter said that he viewed the magnet as a point. So next is my questions for the reporter and opponent. I first asked him that why was there a trend line on page 26? And the reporter said that it's just an approximate line. And the opponent believes that the energy equation is wrong and should be fixed. And next I asked him how was the rotating speed controlled? And the reporter says that he used his hands to control the experiment. And the opponent thinks that initial energy should be fixed. From our point of view, we agree with the opponent at this part because we can build a Lego setup to control the distance and motors better than using hand. So the next question I have for them is whether friction will change during the experiment. And the reporter doesn't seem to think that it is an important thing to consider. And the opponent says that the setup should be changed so we can control this. So this is my report.
So conclusion from report here, 2 minutes.
So about the concluding remark, as the opponent asked it, the effect of the metal is was controlled, but because I use the same fidget spinner, so it did affect. And why it fit the theory? Because kinetic and potential time is linear. Real gear should be spin continuously right, but it's right, but I didn't observe that in the magnetic gear. What are their peaks for the low energy? Just the isolation. And tracker is wrong. And you don't have to control the starting point. You can wait to measure the initial energy by tracker. That's all.
Question from jury. Any question from jury?
Graph of the U and A changing versus time. And my question is that can you give some simple qualitative explanation about why U is a magnetic case of movement and so on, as well as the distance between the peaks, namely in the period of frequency. Is there any changes on that?
What do you mean?
Let's go back to the, something like this, yeah. If you look at carefully on the separation between those peaks, either for the blue or red one, is there any changes there? It seems it's getting narrower and narrower. I'm not quite sure if my reading is correct.
It's getting narrow. The period is getting narrow.
Yeah, I mean, any meaning, any physics meaning behind it.
The meaning is because of the friction. Friction.
And hence,
Right.
so how come that when the blue one is the peak maximum and the red one goes down to the minimum?
The orange one thing, the orange one has maximum gets down because of the friction.
I'm talking about at some particular moment, the blue one goes to the maximum, and meanwhile, the red one goes to the minimum. Please give a simple argument.
It's a fidget. They are fidgets. And when the fidgets, and when you get when they get close, when they get close, they reach the maximum of potential.
And how come it will be minimum for the red one?
Like that. About when the kinetic energy is
That's all right, that's all right. Yeah. I think I got what you want to say. Thank you. Any comments about this?
We're going to try to understand what the graph is trying to show us.
All right. Okay. Some elements. Just the tutorial shows that the total energy is decreasing by time and linear, right? Linear. And as well it won't. And okay. That's all.
Is there any other questions from juries?
You do all the integration to calculate the angle and the potential by yourself. In this graph.
this graph, and
You do the calculation by yourself.
to calculate it by myself,
Yes.
by using the Excel.
Okay.
question, yeah, I will stop here then. So 1 minute for you to calculate the score. Are you ready? So now, first would be the score for the reporters. So it's 3, 3, 4, 8, and 5. And the second would be the score for the opponent. So it's 5, 6, 5, 7, 6. Finally would be the score for the reviewer. So it's a 6, 4, 6, 7, and 5. So now it's 15 minutes for break. Thank you very much.
Thank you.